Welcome back, everyone. So let's get started. So today we're going to talk about multiple linear regression when you have multiple of the explanatory variables, and we're also going to see polynomial regression. So we talked about linear algebra for 3 lectures, and I said, you know, this is going to be kind of important to have linear algebra as kind of the language that we describe kind of algorithms within FoDA analysis. And so today you're going to see 2 very cool tricks that are, you know, essentially I got kind of tricks from linear algebra, and it's going to turn things that are going to look fairly complicated, I think, into into having very simple solutions that you can kind of both think about programming very easily and also expressing kind of what's going on with very simple notation, given that you understand the linear algebra. So great. So cool. So let's look at just where we are in the schedule. So let's see. So homework 2 was due on Tuesday. Hopefully just what everyone is, so turn that in. If you have to turn in a little bit late, you can still turn it in by the end of today. So with a penalty, but you can still turn it in. And then, so let's see, homework 3, we're finalizing. So homework 3, that will be posted by next week, Tuesday. Hopefully we'll have it up by the end of the week. That one won't be due until after fall break, but so this one involved, if you've used Python before, you know, it's probably not going to be kind of too hard, but if you haven't used Python before, you're going to do some stuff that's a little bit more advanced than we've done in the previous homeworks. We're going to go through, we went through an example in Colab on Tuesday. We're going to do some couple more examples today in class as well. And then we'll see another example in Tuesday in class. And so these will be kind of the core basic things you'll need to do homework 3. So you should basically mostly be able to do, well, about 2/3 of it, I would say, you know, if you want to start and do it over fall break, and then there'll be a section on gradient descent in the homework as well that we won't have till after break. Okay, so great, that's something to look forward to, I guess. So also quiz 3 will be the last day before fall break. We have built-in time for like small review or Slack on Thursday. We'll cover all the core material in this section on this lecture and Tuesday next week. But there might be some things like I might not get time today to kind of prove why the solution we get is optimal, and that's kind of might be interesting. You can also just review some of this material because this will be much more new material than we've seen previously, so we can review it. Maybe we can talk about some other stuff. So I'll give you a chance to give me some feedback on what you want to see in that lecture. But there'll also be the quiz 3 on that day. Okay. So let's get into it. All right. So what we'd like to talk about. So today is when our input, remember, I gave the input to this problem. As I said, this was written x, y, right? And this was a series of these data points. We could think of these as x1, so y1, x2, y2, up to xn, yn, right? And so I said, okay, so we're writing x as a capital X and y as a lowercase y. And in the lecture we had on Tuesday, it was the case that all the x's were just kind of these scalar values. So we have that each yi was in R, but today we're going to talk about the case where each of the xi's is going to be in Rd. So we're going to have d-dimensional vectors now for each of these explanatory variables, right? So these are the explanatory, and this is the dependent. Okay, so we're going to assume that the y value can be explained. It's going to depend on the x values, right? So now we're going to think of writing this, so function, right? The goal is going to be a function, and I'll write m here as a model that's going to take in a value xi, and I want this to approximately be the value, so yi here, right? So I'm going to use the xi's to explain this, but now instead of just one variable, like we looked at this example with the height and the height of someone would somehow explain their weight. We can get some explanation or model out of it. Now we're going to do this with multiple explanatory variables. We can have multiple factors that are all going to predict the dependent variable. Okay, so we're going to build a more complex model, not just taking in one factor, but in multiple factors. All right, so there's this d here means that there are multiple factors in this model. So, okay, but for now, for this part of the lecture, we still want this model to be so linear. We're still going to keep it simple. The second half of this lecture, we're going to kind of build on these same ideas, but kind of change the model a little bit and look at, again, one-dimensional explanatory variables with this more complex models on that variable. But now we're going to expand it by saying we have multiple variables. We still want the model to be, we still want this model to be so linear. Okay, so when I want this to be linear, what this means is that I'm going to keep the form my yi hat, which I'm going to get out of this model, and I'm going to parameterize this model by a vector called alpha. Okay, I'll say more clearly what alpha is, but in a second. But this is going to be taking this xi, right? So this is this model. What does this model look like if it's going to be a linear model? Okay, again, I'm going to think of this as m alpha, and this xi is now a d-dimensional variable. It already has an index I, indicating it's the ith data point. So I'm going to write this as xi1, xi2 up to xid. Okay, so now I have two subscripts here, and this is kind of a little bit complicated. I'll try whenever possible not to have to use two subscripts, but that is the case here. We do have two subscripts. We have data points, n data points indexed by I, which data point, and then which dimension. I'll try and index this by j. This is up to 1 to d. Okay, and so if this is a linear model, then it's going to have the form. If you remember before, our line line was, this was AXI plus B, right? So this was the linear model for the line, and I just had these coefficients, the coefficient A and this offset B. Okay, we're going to do this, but we have more going on here. So I have more kind of input variables to deal with. So I'm going to write this as alpha 0 plus the sum j equals 1 to d of alpha j times xij. Okay? I can write this out kind of in this other way. I'm going to have alpha 0. This is just the same thing. Alpha 0 plus alpha 1 xi1 plus alpha 2 xi2 dot 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 alpha d xid, right? So I can, it's, so okay, so this is a linear model still, because now the model parameters are these alphas, which is the same alpha as here, right? And the only thing I'm doing with these model parameters is it's just a kind of a multiplication times one of these input parameters, one of the explanatory variables. I'm just multiplying I'm adding them together, and I can add this offset here too, right? So this is still what's called a linear model, right? So this is a linear model still. Okay, we'll see a polynomial model later on in this lecture, and you'll see how it's kind of more powerful here. But everything I'm doing with the explanatory variables is I'm just multiplying them by some coefficient, and I'm adding these things up. Okay, so we're gonna find a model for this data now, but restrict it to this form. Okay, we're gonna restrict it to this form, which is a fairly simple form still, right? All I can do to each explanatory variable is I can multiply it by something, and I can add these things together. Okay, there's one other way I like to write this, which will be very, very useful, is to think of this as I can encode this as actually a single, dot product. The dot product strikes again, where I have alpha dotted with this vector 1, xi1, xi2, up to xid, okay, which is going to be equal to, I can think of this as the dot product of alpha of 1 with xi. I just concatenated these things together. Okay, and so what is alpha in this case? Alpha is going to be alpha 0, alpha 1, up to alpha d. Okay, so what is the dimensionality of alpha? I can think of alpha as a vector now. What's the dimensionality of alpha? So d plus 1, yeah. So this is not a d-dimensional vector. This is in d plus 1 because I've got this extra term alpha 0 here. And so this matches up with this 1 vector here too, right? So I've taken my d-dimensional vector xi and I've turned this into a d plus 1 dimensional vector. Okay, and once I do that, though, the advantage is now the model is just a dot product. Okay, so it's only a dot product I have to worry about here. In fact, yeah, I'll walk through an example of doing this, and then we'll kind of see this a little bit more clearly. But what's happened here is I can turn my data point, the data point I have to worry about as my explanatory data point, as just a vector of values, and my model is then just like this. The model is then just taking this dot product, just this multiplication step here. Okay, so this one, the interesting thing is this one here kind of appeared out of nowhere, but I can realize that there's actually a hidden value 1 that's right here. Okay, so there's actually this hidden value 1 that was sitting right here the whole time, and this was also true in this line, right? I can also put this 1 here in this line. I could have said, when I had the line model, I could have said, well, b was multiplied times 1, and so really this was also a kind of it could have been a dot product also. Okay, we wouldn't have had that simpler solution that we saw on Tuesday if we wrote it in this way. But here now we've reduced it to a dot product, and we'll get a more general solution, which will say, okay, the model is just a dot product. I have data, right? My data here is this part that I've highlighted here. This is now this data point, right? And I just have to take a dot product with the data point to evaluate this model. Okay, so I've kind of simplified kind of this model down to just a dot product. It could have been I multiplied and I added stuff, but the dot product encodes all of that together. And this will kind of simplify the mathematics we see as we look towards the solution for finding kind of the optimal alpha, which is what we're going to want to do next. Okay. Okay. So there's a lot that's written up here. Hopefully, all the steps individually were pretty simple, right? Our model, we're going to pass as the input this vector xi, which has d coordinates, right? We're kind of going to convert it into d plus 1 coordinates with the extra 1 here, and then this model is going to actually just be encoded as a dot product. So the model depends on alpha. That's why I wrote this as m sub alpha here, right? Because the model depends on it. Our choice of model will be parameterized by alpha, and we need to, if we can determine what alpha is, we know we can describe this how to evaluate this model. Again, just a dot product here. Okay. Let's see, questions in the chat. Oh, great. Okay, good. All right. Okay, let's go through an example here. All right, so here's an example. This is supposed to be drawn from the idea that there is a website, and it's trying to track its customers on the website. And this is not too different from what websites actually do. And this website is selling some products, and they want to know what the sales are from an interaction with the customer, right? So I'm going to have, I think there are like 11 rows here. Each row here is one customer, right? So this is one customer, and its sales was in cents, right? So this cents means that this was actually $22.01 is how much they spent on here, okay? And I'd like to track some characteristics of the customer to figure out, try to understand based on some characteristics I can track, kind of predict how much they're going to spend on the website. This will help me change the website design, all right? And so there are 3 things I'm tracking. I'm not just tracking one thing. The first thing I could do is maybe just look at the amount of time that they spend on the website, right? So I could look at just the time they spent on the website here, right? And this may be the amount of time in in seconds. So if they spend 232 seconds on the website, Well, they're probably browsing the various things on the website. Okay. So maybe maybe you think, hypothesize, the more time they spend on the website, it's more likely are to spend something, and maybe to buy multiple things, so they spend maybe more money, or they dwell on a larger purchase. Maybe also, so the second column I call, so jiggle. This is something that's actually measured. You have a mouse or you're moving your cursor. How much do you move your cursor around, right? What's the total length of the movement of your cursor while you're on the website? If it's open in the background, you're not really looking at it, you're probably not moving your mouse around at the same time. So if you move your mouse around more, then this indicates a more interactive time on the website. There are some so CAPTCHA things now where it says, so prove you're not a robot by clicking in this box. Okay, well, the robots, you know, kind of a program surfing that website can click in the box, but what they have more trouble doing is how they move the mouse towards clicking the box. The website will identify the box and move the cursor in a straight line to click on it, probably. But a human will probably move the cursor around in a weird way and kind of jiggle it a little bit. Even though you don't notice it, but you're not quite moving in straight lines. And they can kind of tell that difference is one way of detecting if you're a robot. And the similar thing on these websites. You can measure the engagement on the website based on how much of jiggling of the mouse. Right, so this is another category which is tracked. And then the other one is how much are you scrolling down the website? A lot of these are infinite scroll or something, or as you go further down, you see more and more products, right? How much is the amount of scroll you have going to predict this amount of sales? Okay, and so I can capture these multiple things and they might have an interplay. Maybe if I scroll more, I'm not jiggling and those kind of make up for each other. Maybe the time is good as long as I'm actively doing some jiggling and scrolling, but if I just have it open but I'm not interacting with it, well then that's not as helpful actually. Okay, so how do we build a model that understands kind of how to predict the sales without kind of combining these different features and understanding a richer model of what is going on here? Okay. So and we're gonna just build this linear model, okay? And so, all right, so what do I wanna, what else do I wanna say about this? Okay, so kind of the first thing that we're going to want to do is to basically think of adding this extra column onto here. Right, we're going to have kind of this offset column. So I'm going to convert this into, and I'm going to call this like the x0 dimension, right? These are x1, x2, and x3. We use meaning the columns of the matrix, but I want to add an offset one that puts a 1 in every entry here. Okay, because I'm going to build a linear model, right? Where it's basically to predict this, I'm going to say alpha 0 times 1 plus alpha 1 times the x1 value plus alpha 2 times the x2 value plus alpha 3 times the x3 value is going to be approximately equal to this y value, right? Right, so I'm going to want to build a model like this. And so if I want to build this as this dot product model, I need to add this one column here in front. Okay. And so in order to do that, I'm going to kind of think of building a matrix, right? Here, right? So remember I said the input was an uppercase X, and we try to use uppercase X's as matrices here. So I had initially, if I go back to here, I had basically, this is the input matrix I thought of as X here, right? But then I'm going to convert it into this green matrix, which is a bit bigger, and I'm going to call that X, so tilde. I'm going to put a little squiggly line on top of the X, and this is going to be an offset here, right? So this guy was in 11 by 3, and the X tilde is going to be a matrix that's in 11 by 4, because I've added this extra dimension in front here. Okay? So I'm going to build this X, so tilde dimension, this X tilde matrix here. Okay. So let's, all right. Okay, and then similarly, I'm going to kind of think of my Y is going to be a vector here, right? So this Y is in R11, this 11-dimensional vector. Okay, and so ultimately I want to build a model. My model is going to depend M alpha kind of such that we're going to be able to write that Y should be approximately X tilde times alpha. Okay? So now it's, instead of just saying, this was equivalent to saying, say, for all I in 1 up to n, I wanted yi to be approximately the dot product of x tilde I times alpha, right? But I can say it with the whole matrix here, right? I'm saying that this whole y vector column on the right will approximately be this matrix multiplied by alpha. I can encode this all in linear algebra this way. It's the output of x tilde alpha is going to be a n-dimensional vector, right? And I want the whole vector to match. Right? And so I can solve this, and we'll talk about how to solve this next. Okay, I solve it, and I'm going to get alpha is going to be alpha 0, alpha 1, alpha 2, and alpha 3, right? So it's going to be these three values, which are, I drew down here. They're going to react in this way. Okay, so I can solve for these three values. Okay, and so I've pre-computed the solution for this data set. So let me just write this up, and we can maybe think about how to interpret it. Before I tell you how to do it, I think it's important I tell you how to interpret it, because one of I think something we work hard on in developing this kind of data science program is we don't want to just give you tools and set you loose on the world. We want to let you know how the tools work and how to interpret them, so you don't go and do something stupid with them. Okay, I'm serious about this. There's a lot of people who are using these powerful software and tools without really understanding how it works. This leads to a number of problems. Sometimes it's just that they are doing it wrong and they're drawing completely wrong conclusions, and it's not helping whoever they're trying to help. The other issue is that it's actually making predictions that cause problems in the world. There's kind of a lot of the there's like these big automated systems that's like predicting, that's like text completion and stuff, and this has encoded lots of horrible biases into it. There's the way that information is being filtered to try and prevent misinformation on the internet. And I don't think they're making decisions and how they're doing that I don't think are working how they publicly describe that they are working. I think they know better, but I'm not 100% sure that they know better when they're doing some of these things. Okay, so let's describe how to kind of interpret these things and how not to interpret these values. Okay, so I guess I'll put alpha is 26, 226 26. Remember, this is times 1, so it doesn't have any units. So this is basically, if someone's on the website, I guess I expect them under this model on average to expend, with, if everything else was 0, to expend like $26. Okay. Alpha 1, okay, this is how much I scale the time, or I convert a second on the website into a cent, is 0.42. Okay, so this is a smaller number. Alpha 2, this is 12.72. This is a centimeter of jiggle on the website corresponds with about, so 12 cents. Okay, and alpha 3, the amount of scrolling, it's negative 6.5. Okay, so a centimeter of scrolling corresponds with actually losing expected time on the, kind of losing the expected amount of sales. I lose 6 cents for every centimeter that is being scrolled. So, okay. So how can I interpret what these means? Okay, I gave a little bit interpretation. I said if everything else was 0, right? If the time spent on was 0 and the jiggle was 0 and the scroll was 0. So if I just got someone to log on, then I can say, was my expected return $26? That's what this first one is saying here. Okay. Okay, so I can say, I can interpret this if I know everything else is 0. Okay. So this one I can interpret because it makes sense for the potentially the time, jiggle, and scroll to be 0 right when they log on, and then that changes over time. And then I could say, well, if I didn't know the time, what's the relationship just with if everything else was fixed? If I didn't know the jiggle time and scroll, or if I didn't know the jiggle time and offset, I could say the scroll, well, maybe that's decreasing this. Maybe this is decreasing the amount of money I'm getting. Okay, but this is a little. I'm getting into a kind of a dangerous zone if I try and make this conclusion, because I already know that the first coefficient is not 0, so it's not independent of this. What this is doing is it's a joint model, okay, but it's not factoring in the joint probability in between these things. It says these terms, I'm building a model assuming these terms are completely independent of each other. Okay, so I shouldn't say, but the data is not necessarily independent of each other. If I can't have a lot of jiggle and scroll if I don't spend more time on the website. So if 1 increases, the time where they spend only 2 seconds on the website, well, then the jiggle and the scroll is also very small. Okay, so these are correlated. Okay, so, and this is a model that's trying to build what's the best prediction. But if things are correlated, then there's multiple ways you can kind of understand the factors. So I should not say something like, well, the alpha 1 term, the amount of time on the website is not important because this coefficient is small. If this is small, then I shouldn't say I should not pay attention to it. It just means that, well, I fit a slightly better model by maybe looking with the correlated factor, which was maybe the jiggle. Okay, and maybe this is like a small correction term to that. But if I didn't have the jiggle, maybe I could have fit a similarly effective model with just the time. Okay, so I don't want to draw conclusions of which is most important, which is least important, which is kind of the feature importance of these things. This is very commonly done. I was at a PhD defense or a proposal where someone was proposing to do this, and I said, nope, that you're going to draw incorrect conclusions if you do this, and we had to kind of revisit some of these things. So be a little bit careful about interpreting these beyond the model as a whole. Okay, what you can interpret, and which we'll talk about a little bit this lecture and much more in the next one, is how effective this model is kind of kind of in predicting some new data, but as a whole. You want to treat it, you want to look at kind of the model as a whole, right? As a whole and how its effectiveness. It's hard to read too much into the individual attributes. Okay. Let's see. Okay, overfitting is So overfitting is bad. Incorrect data fitting practice also bad. Among other things, data is powerful and should be used carefully. Yep, great. Yeah, we'll talk about overfitting and related issues in the next lecture. Okay, good, good. But that's not quite what I'm talking about here. It's just the interpretation of these numbers. Okay. All right. Let's talk about how to actually solve this. Now, I promised there was going to be a way to actually get those values, and we'll hopefully see it in Python as well. Okay, so let's kind of write down this algorithm again. Okay, we have input x, y, where x is going to be an n by d matrix, and y is going to be an n-dimensional vector here. And what we'd like to build a model M alpha xi, which is going to be equal to alpha 1 xi, just a dot product here. Okay, so this is our simple model. And so again, okay, so in order to talk about how do we solve this, we have to say, how do we measure the optimality of the model? Okay, we're going to go back to our sum of squared errors, right? And this is again going to be a function of x and y and this model M alpha. Okay, and we're going to be able to write this again. This is going to be the same thing as we had when x was one-dimensional, as just the residual squared. Okay, just the residuals. And the residuals are defined in exactly the same way as before, right? We were careful to set this up, so it's going to generalize to these more complicated models. Okay, where this residual is exactly the observed value yi minus the predicted value, right? We sometimes call this guy yi hat. Okay, and so this is the predicted value. Again, we're only measuring error in this y coordinate. So this is some sort of model we're introducing, and we're predicting y, and we don't need to worry about how close are the model points to kind of the data point in this. You could think of it in a d plus one-dimensional space to that model. We don't need to worry about the geometry of this because this is now more complicated. And it's going to get even more complicated in polynomial and other sorts of regression models. We only need to worry about how well it does on the prediction test in these residuals. And so this is our goal, to find the alpha that is minimizing the sum of the squared errors, right? So the goal is then going to be, let's call this alpha star, which is going to be arg min over alpha in rd plus 1, where I can, it turns out you can write this as a function, say S alpha, which is going to be the sum of the squared errors of x, y, M alpha, okay? So x and y go into this, so is the model, but I really only care about the parameters in alpha. I want to find the model, the alpha star that minimizes this, and this encodes my model up here, right? Because this model is just defined by this alpha parameter, right? If I just have that alpha parameter, I can evaluate this model. Okay. And so in order to do this, again, I need to convert. The first step is going to be create this x tilde matrix here, which is going to be a kind of this matrix X where I'm prepending this column of all ones here. right? So this guy is, right, like this. This is the all ones vector here, right? So that's adding this all ones vector, this green column of all ones in front here. I get this X tilde matrix, which is now in Rn times D plus 1. Okay, right? So I've expanded the dimensionality here by 1, and that's good because alpha, again, my goal is in D plus 1. Those are the same. Okay, so we're almost at the solution. It seems like we haven't done anything yet, but we're almost at the solution. I can just write down the solution now with linear algebra. Alpha star is going to be X tilde transpose X tilde, this quantity inverse times X tilde transpose Y. All right. We've done it. Okay, this is our optimal solution. This piece of linear algebra here, I'm multiplying some matrices together, taking an inverse, multiplying another matrix, and multiplying by y. I get the answer. Okay, so this should be something, you know, we'll often just pretend that this matrix is X without the, we'll just, and drop the tilde. Okay, so, you know, if you drop the tildes in front here, or you don't want an offset, this might be a little bit cleaner. Just to read, because it's not too complicated. I expect you eventually to just like have this memorized, right? This is it's not too complex of an expression. You should eventually just memorize this is how you solve for this optimal value with yeah, okay. So this is kind of, this will just a little bit easier to see here. Okay. So this seems a little complicated, but it's actually pretty similar to what we had before. Remember, we had this one-dimensional solution. Remember, the one-dimensional solution for A was something like this normalized X dot product normalized Y times the 2 norm of X, which is just the dot product with itself, right? So this was the solution for the slope before, right? When we solved this one-dimensional case. Okay, and this is actually pretty much this same, there's very similar thing going on here. This divided by X squared, X times X. Well, that's really this term, and then this kind of division, this division part is this inverse. Okay, so when I'm dividing through by that, that's kind of what I'm doing with the inverse. Remember, I couldn't divide by a matrix, but I can multiply by its inverse. And so that's what I'm doing here. And then the X dot Y, well, that's, you know, that's the part that's this X dot Y is the same as this numerator here, right? So it's basically the same model. I didn't need to kind of center the data because I don't have an offset. That was some weird thing I had to do to deal with the offset, then solve that separately. Because I've appended this first row here, I don't need to solve for the offset separately. And I don't need to do this centering of the data. Okay, so it's kind of actually simplified the solution, in fact, by having this 1 here in front. Okay? Okay, and this is kind of a closed form solution as well. The reason it's not in completely closed form, I mean, you can type it into Python and it will just call kind of the functions that computes these things. But this matrix inverse is a little bit of a tricky operation. If you've taken at least numerical part of a linear algebra kind of course, you'll see that the matrix inverse it's not something you can just compute the same way you can like a matrix product. We'll actually see how to compute it later on in the semester, one way how to compute it with a very simple algorithm. And it's kind of, it's not quite closed form, but you can kind of pretend you can close your eyes and pretend you just type this and it just works. Yeah.
So will x tilde, like x tilde cancel to y x tilde, that always be invertible?
It will not always be invertible in most. it is yeah. So this is a really good question. It depends on. Okay, so what is the dimensionality of this, right? So this is a great question. Let's say x tilde t x tilde. What is this? Is in R what? Okay, so what's the dimensionality of this matrix? It's square, so it's like m by m. But what is the value m here? And why is it square? So x tilde transpose, right? X tilde was n by d plus 1, so x tilde transpose is d plus 1 by n, right? So the first dimension here is d plus 1, and this one is n by d plus 1, so the second term is the n's kind of collide, and I get this to be a d plus 1 cross d plus 1. Okay, good. So it's square. That's good, but I need to be full rank, right? Usually we'll have a lot of more data points than we will dimensions. That's the setting we're typically in, and that's typically going to cause the rank of it is kind of the minimum of the number, the kind of this, the dimensionality of the span of the rows or the columns. Usually there are a lot more data points than columns, so typically they can't fit in a d-dimensional subspace. That's typically the case here. And with noise and if there's data noise, I didn't capture the seconds exactly, it's very hard to get things that are exactly low rank. And so then this will be full rank, and then I can invert it. This can be an issue, and sometimes we'll add what's called like a ridge term to make it so it's so it has to be invertible. We won't cover that in this course though. It's a really good question. We'll see how to think about that actually a little bit later when we talk about gradient descent. We'll think a little bit a different way about what it means to be invertible, or an issue which is related, and we'll see some geometry about how adding data kind of tends to make this, more stable. But yeah. Oh, good answer. Okay, good. So, okay, yeah. So this typically is going to be invertible unless the data is like really oddly constructed, or you don't have enough data points, and that's another issue. And we're going to assume we have enough data points. Like if I had fewer data points than I had dimensions in my model, this would be a problem. So we're going to assume we have way more data points than we have dimensions. And we'll talk about that a bit next Thursday's lecture as well, some of the consequences of that. Okay, cool. Okay, so this is the solution. I now have a simple, almost closed form solution for this with any number of coordinates. I could have done the one-dimensional version like this as well, and that would have simple, but then I have the matrix inverse, which might be a little bit of a pain to deal with. Okay. Cool. All right, so yeah, let's not talk about why this is true now. I'll just say you can kind of take you can write down this expression, the sum of the squared errors, and you can kind of take all the partial derivatives and say those have to be 0, and then solve for them, and you get this alpha star in this way. If maybe on next week, Tuesday, we can go through that math and then see some geometry of how to think about this. That's an option, but I don't, looks like I'm not going to have time to kind of go into any detail on that in this lecture. Okay. Okay, so yeah. All right, so that's how I got these numbers. And oh yeah, let's quickly jump. There's example in Collab. This is again linked off the web page. I've loaded in this exact data here. right? This is the same data set again. I print X, I print Y. It always prints Y as a row vector. So don't freak out about that. That's Canvas or Python doing its thing. And right, so how do we compute this? We take the inverse of X transpose. I call this matrix X, right? I put the ones in front here. Typically, I'll do that so you don't have to worry about how to pre-process it. And I put the ones in front here. And so then I just have X transpose X. I invert that. I multiply X transpose again and by Y again. And I run it and I get out my alpha values. This is exactly how I got those values on the that I wrote up on the slides before. I wrote them in the scientific notation, a little harder to read, but that's what they are. As you'd imagine, there are several built-in functions to solve for this. One that takes it in the same form I have here is called the least squares, and it's part of the linear algebra package. It's complaining I didn't pass in some flag that they recently turned on, but again, it gives me the same answer. Okay, and I can, yeah. So that's a kind of again a way how to solve this, and okay, and then again to evaluate it, I can evaluate at a data point. This is one of the data points in the model. This was the third one down, so the index 2. And then to evaluate it, to get the prediction of the amount of money I would spend, again, it's just a dot product. I have my A vector, short for the alpha, and I do A dot x3, and I get out the solution. I predict that it's going to spend $81.93. What did they actually spend? They spent, looks like $2.31. Wait, oh no, third one. They spent $76.50. Okay, so that's not too bad. Okay, I predicted 83. They spent 76. This was one of the bigger purchases, and I did pretty close on. Okay, cool. Okay, so that's pretty simple to do in Python, right? It looked like this weird kind of linear algebra equation, but you know, it's just a bunch of commands. It's one line, right? And there's a way to do it with like a single symbol, in fact, right? Okay, let's talk about polynomial regression now. Okay, so it might seem packed to put these in the same lecture. We just spent a lot of time developing this multiple linear regression, and now we're going to change to a whole new model. And we have to worry about a whole new algorithm and example, but it turns out it's going to be a really simple extension once you know this multiple linear regression. Okay, the big thing to understand here is this model. Okay, when I say, again, okay, in this case, I'm going to say that my input, I'm going to simplify the problem a little bit here and say the input x, y is going to have, x is going to be in R n by 1, okay, and y is going to be in R n. Okay, so I'm only going to have, that means each xi is in R and each yi is in R. Okay, so I'm back to the case where x is one-dimensional. You can do this with this multi-dimensional. You'll just need to kind of combine these ideas together. This will keep it simpler here, and we'll be able to draw pictures again because it's one-dimensional. Okay, but what I'm going to change now is that I'm going to make the model more complicated, right? So I'd like again to have my y hat, my prediction, yi used to be approximately the same, and this is going to be m, and I'm going to call this, I'm not going to put an alpha down at the bottom, I'm just going to use a subscript here too, because if I use a superscript, you think it's a power, but I'm going to have a subscript here, for xi, okay? And in fact, we're just going to write this as y, let's say y is approximately y hat m2 x. So I'm going to drop the I subscript here because we're not going to need to explain the model here. We're going to want to use this subscript to do something else. Okay. So this model is going to be a polynomial model, and the 2 is going to say I want it to be a polynomial of degree 2. Okay, and what this means is that, again, it's going to have an offset plus a linear term, x. Okay, this is a linear model. It's the same thing we did before. And to make it a polynomial model of degree 2, I'm going to call this x squared. Okay, so this is now a polynomial model of degree 2. Polynomial model of degree 2, okay? Right, and if I wanted it to be degree 3, right, I could do alpha 3 x cubed. Right, so I'm taking this input and I'm still, so the model is saying I'm still just learning these simple coefficients, right? The things I'm learning in these models are still these alpha terms here. Okay, but but the difference is I'm taking this explanatory variable and I'm taking this to be, I could be powered. It could be that, so I'm saying that the rate of increase, so say if it was like with this website example, as the amount of jiggle kind of increased, I got really excited. I started kind of shaking my hand a little bit. I'm like, I'm really going to make this big purchase. Well, that really kind of polynomially, the amount of price really polynomial increases with that. So as you start getting bigger and bigger, it really accelerates the amount of price. Okay, so this is kind of this other model. We'll see some pictures of this to kind of help you jive this in your head. In general, I can write this as MP. Use P is the degree of the polynomial, and then I can write this as alpha 0 plus alpha 1 x plus alpha 2 x squared plus ... plus alpha up to alpha p x to the power p. So I can make this as complicated, a higher and higher degree polynomial, as complicated as I want. If it was any polynomial function that, it was some other thing where the maximum degree of any of the x values, but I wrote it as like with some parentheses and I'm multiplying stuff together, but the maximum degree was p, I can always simplify it into this form, right? So it's sufficient to solve in this form. And I can write this as alpha 0 plus j equals 1 up to d of alpha j x to the power j. Or another clever trick, I can get rid of I can get rid of that offset term by just starting at 0. Okay, if I start counting at 0, well, alpha 0 is, then that's alpha 0, and what's x to the power 0? It's always 1. Anything to the power 0 is 1. Okay, so that I can do that as well. Okay. Okay, so this is my polynomial model here. Okay, and what's cool about this is actually a dot product, alpha comma 1 x squared up to xp. So it's still a dot product model, right? Okay, so even though the model is more complicated, I still can evaluate as a dot product, but I have to kind of convert it a little bit first, right? Before, I already converted my x by adding this 1 in front before I took the dot product. Now I just need to do a little bit more conversion here. Okay. And I get the same sort of kind of model as before. It's still just a dot product to evaluate, but I need to convert my data point x into this longer p plus 1 dimensional vector here. Right, so now alpha is in our p plus 1. Okay. Okay, so yeah, so let's look at this example before we go on how to solve for this. Okay, so this is the height and weight data I had before. Let's see, I found some new data. Okay, the below the bar is some new data I found, and now I've plotted this. Okay, so you can see, okay, so this red line I plotted on just the first part of the data. Actually, this is, I ran this on all the data. That's my linear model. Okay, but let's say I wanted to do a degree 2 model. A degree 2 model needs to be like a parabola. Okay, now I don't need the whole parabola. I just need a piece of the parabola to try and fit this. And I might get a model that looks like this. I don't know, might be slightly, well, maybe this way looks slightly better. You can imagine this kind of going off and you know, becoming a parabola of like go off to the left, it bottoms out and comes back up. But I only care about how it fits the data. Remember, I don't want to extrapolate so much. You might want to mentally think, does it make sense with the height and weight that grows kind of with this rate? And maybe that's the right thing. If I have a cubic model, right? So let's, this one, this was with p equals 2. If I get a cubic model, and we'll actually run these in Python in a couple minutes, a cubic model, this one is allowed to go up and flatten out, and then I'm allowed to do this, right? The quadratic model must, the extreme endpoints, they must either both be positive or both negative. With the cubic model, the left endpoint can be negative and the right one positive, or vice versa. But I want it like this, and it kind of can do a little dip in the middle, and this fits pretty well. As I increase p, I can fit more and more complicated model. As well, I'll try and show you if I go to like p equals 20, I can do p equals 20. What do you think a p equals 20 model is going to look like? Ah, okay. So one guess is that's just kind of like kind of a line that's kind of fitting these dots exactly. This is not how it's going to look. If you haven't seen this before, you might be kind of surprised. It'll actually look like it might do something weird like that. It'll go through all the points, but what it does in between will be kind of weird. Okay, so this might be p equals 20. It'd be great if it fit through all the points, and there's kind of, but that's not typically how it works. I'll try and talk, yeah, over the next, before we finish this section, I'll try and give some insight into some kind of really recent ideas that kind of tries to get the p equals 20 model to actually look like what you're describing, and but that's kind of stuff from the last few years, almost 2020. Yeah. Okay. Great. Okay. So let's see how to solve this, and then let's jump to Python, and we'll see how close my hand-drawn pictures actually look like here, and I'll show you how to solve it in Python. Okay. So okay. Again, we have input is going to be x, y, and this is going to be in r n by 1 cross r n. Okay, and the goal, and yeah, and we want our model p. Let's call this alpha p, because we're going to need to fit some alpha here. Alpha p of x, xi, I want this to be approximately yi, and m alpha p is going to be of the form alpha of 1 x up to x to the power p. Okay. And so again, our goal is going to be this alpha star, which is going to be an rp plus 1, which is going to be the arg min over all these alpha, again, rp plus 1 here. Get rid of this, okay? And that's going to be some sum of squared errors. Right, so again, we're going to use the sum of squared errors, and we're using it. There's a way to derive this assuming it comes from this model with some Gaussian noise, but we don't ever verify that. So really the reason is that there's this algorithm we'll be able to use, this very simple linear algebraic approach to it. And again, this is the sum over I equals 1 to n of yi minus model alpha of p at xi squared, right? So this will be what our sum of squared errors is, and we want to solve for this alpha star, okay? And so how do we solve for the alpha star? To think of, the first step is I'm going to convert each xi, right, it's an element of x, and I'll just call this into a vi, which is going to be an rp plus 1, okay? And vi will be equal to, again, 1 x squared up to x to the power p. So this will be, yeah, so x to the power p here. And then we'll just stack these together. We'll call this x actually tilde p, okay? And this will be v1, v2 up to vn, right? So this is equal to 1 x1 squared up to x1 to the power p, 1 x2 squared, x2 to the power p up to xn squared, xn to the power p, right? So I'm going to create this matrix from this, which is just these rows here, and I'm going to have my y that I already have, and then the solution, okay? Does anyone guess what the solution is going to be? I'm going to get alpha. I can now just write down the solution. And see what I've done here? I convert this into a matrix. It looks kind of like before. So I can just do xp tilde transpose, xp tilde, this quantity inverse, xp tilde transpose y. There, done. Boom. Right? So that's my solution. Once I've converted it into this form, I've done this expansion. I've expanded my explanatory variables. I'd say they're explanatory, but you know, these other, the squared version and the p version are also explanatory. Okay, and then I get this little bit bigger matrix, and then boom, I just plug it into this expression. Okay, the same thing we did before, it's just, I got there a little bit differently. Okay, so, you know, again, the algorithm kind of, because we're doing sum of squared errors, we get this very, very simple, straightforward algorithm here. Okay, that's pretty cool, huh? So the solution wasn't, you know, with linear algebra, you know, I can write it in this one line. And I mean, and linear algebra is in Python. You know, is it built into Python so I can use it in the language of Python. Before we do the example, well, let me do, I think there's, let me do a smaller example. We're going to do an n equals 3 example where x, I just want something to be completely clear. Y is 1, 6, 5. I just want to say, well, what is this expansion? What is x, in this case, what is x p tilde, let's say with p equals 5. Okay, what is this expansion here? Let's just work through this example. I want this to be clear because this can be a little bit confusing. So what is the first column going to be? It's ones, right? And there are 3 of them. 1, 1, 1. The second column is just going to be a copy of the original x. That's 2, 4, 3. The third column, okay, I need to do 2 squared. That's 4. 4 squared, 16. 3 squared, 9. Right? The next column, this is the cubed version. So I have 8, 64, 27. And let me just write the other ones up, right? 256, 81, 32, 10, 24, 243, and y is the same as it was before, right? So this is how I do this expansion. Just so now, hopefully this is, you know, it's not too hard to do, but now you see kind of a hard example of what this looks like. Once I've done this, I just plug it into this expression. Again, alpha star, just so you see it one more time. xp tilde transpose, xp tilde, it's quantity inverse, xp tilde transpose y, right? That's my solution. Okay, I'm not going to write out the answer for that, right, once I have it, I can just plug it in here. Okay, let's go see how to do this in Python, okay? All right. Okay. Let's see. Okay, we're going to do some plotting. So we use my matplotlib library here and NumPy. So let's load those all in. Okay, I'm going to, for this, I want to have this be a little bit more interactive. So I built a function. Okay, so if I want to define a function in Python, you just do def some function colon. The spacing and the tabbing is important. All these will be tabbed in if they're inside the function. Once the tabs run out, then you're outside the function again. Okay, so I'm going to define a function that's going to do my scatter plot. It's going to set the axis. So all these things look the same. They have the same x and y axis no matter what I plot. Okay, and I'm going to do this linspace to create this curve I'm going to plot now. It's not going to be a line, it's going to be a curve, and so I set it between 60 and 76, and I'm going to have 101 spacing points, so it's a little bit smoother than I did before. And I'm going to find the coefficients with this built-in function called polyfit. Okay, yeah, so I can make this a bit bigger. Maybe too big. Okay. With polyfit will allow me to pass in a parameter p, which says what degree my polynomial is. And it's a nice function for this sort of demo because it's going to output this fits, which are going to kind of be this function I can evaluate. And then I can evaluate that function at all the s values in my linspace, right? All the x, those are the x values I want to evaluate at. And then I draw this red line with the line width you'll be able to see. And I'm going to plot it. And this is how I put a title on my plot. Okay, so this is just a function in Python that will do the plotting of the points and these things. And so, okay, so now if I have my, okay, I've passed in my data. This is all the height and weight data we had before. Hopefully those are the same or close enough. And now I can run polyfit, and this is this curve. Let's start with 1 here. Okay. Okay, and let's see what happens. Right, so in 1, when I put p equals 1, I get this line, right? I promise this line, this linear fit. Okay. Okay, if I do p equals 2. Okay, it looks a little bit different. It looks kind of like this line, but it's curving up a little bit. There's a little bit of a parabola going on here. This doesn't a substantially better fit. The error might be a little bit smaller, but okay, p equals 3. Ah, there we go. This one looks nicer, right? It's kind of a third degree polynomial can start low, it can kind of level out, and then it can expand again. If you're thinking of height and weight, maybe this actually makes sense too, right? Weight is a measure of kind of like the volume and mass, and the height is a one-dimensional thing. So I might have the height cubed, right? That's how you get volume. So this maybe makes sense. I don't know if this is data I made up, so don't kind of go hypothesizing about kind of the height weight curve and population from this data itself. But in general, three-dimensional term kind of has some kind of physical meaning. Okay, let's do 4. 4 looks pretty much the same. This function will eventually, I think it goes down to 0 on both sides. So if I go way off to your right-hand side, it'll eventually start curving back down again. But we care about it in here. Let's try 5, see what happens. Anything better? It's about the same. It's not really helping. What happens if I do let's try 10 first. This 10 is starting to look like it's trying to go through every point here. It's getting most of these points. Not quite all of them, right? Some of them it misses, right? Over the right-hand side. Can't quite go through those points. Let's try going up to 20. Okay, this isn't so bad. I haven't quite gone through all the points yet with 20, but I can see that this function, as soon as I get past that last point, it kind of drops off like crazy. It's also starting to give me these warnings, and this is because it's inverting a matrix, which it probably shouldn't be trying to invert. It's getting pretty close to being lower ranked than it's supposed to be. Let's see if I go up to 30, what happens. All right, it's still not fitting through these points. I think Python, this function has some safety mechanisms built into it. If I go to 30 and I actually evaluated it not with this polyfit function, which has some mechanisms built in to prevent it from actually instead of inverting a matrix, it's doing something else, and because it's not actually invertible, but that's also preventing it from actually fitting through all of the points as well. If I were to do I guess this might be a fun thing to do on your own. Go and actually implement this where you do the expansion yourself. I might ask you to do this in the homework. Run the expansion yourself and then invert the matrix and in order to solve it. And then it should actually go through all the points, but it will start getting kind of crazy like I'd mentioned. Okay. A lot of times these libraries, they try and build in stuff to prevent it from looking too crazy. But then you might not really know what it's doing, right? I should not be able to compute this with 30. I should not be able to, because it's basically inverting a matrix that is lower rank. It's a 21 by 21 dimensional matrix. No, it's a 31 by 31 dimensional matrix, but its rank, it can be at most the number of data points, which is like 20. Okay, so its rank is at most 20. It shouldn't be able to do this. But this function is saying, well, it's probably adding kind of some small factors in the matrix, so it is invertible. But then that prevents it from actually fitting through these points exactly, which you might want to do. Okay, so we'll talk about other consequences of trying to fit through these data so much, and we'll see which one we think is better. But that'll be the lecture on Thursday. Great. Okay. Yeah, that's the end. Oh no, next week Tuesday, not Thursday. This is Thursday. Okay. Well, but we'll stop there for today.